Okay, welcome to the Saturn Notes review. Just a quick little video that's going to hit some of the highlights of the planet Saturn. I'm going to do another video for Uranus and Neptune, and you can check those two planets out on the same video. Saturn is the Lord of the Rings. It's not the only Jovian planet with rings, but it is the most well-known planet that has rings. So, it's my favorite, obviously. It's got an orbital period of almost 30 Earth years. It takes a long time to go around the Sun. It's about a third the mass of Jupiter. I mean, again, these numbers, you're not really needing to take that into consideration, but it's less massive than Jupiter. That's what you need to know. It takes longer to go around the Sun than Jupiter. I mean, this should make sense using Kepler's laws. It's further out. It's 95 times the mass of the Earth, so it has a lot of mass. It also has a lot of volume, though, so therefore it makes it low density. So it's a big planet, but not near as much mass as something like Jupiter. So it would technically float in water because it has a density less than water, which is water has a density of 1 gram per 1 gram per milliliter. Rotational rate's about 10 hours and 40 minutes. It rotates differentially. All Jovian planets rotate differentially. This one rotates slightly slower than Jupiter. If you remember, Jupiter rotates about 9 hours and 50 minutes. And remember, differential rotation is the idea that it rotates faster at the equator and slower at the poles. The rings are easier and harder to see depending on Earth's orbit and Saturn's position along the ecliptic. So sometimes you see in this video or in this picture down here, sometimes they're kind of hard to see because it's kind of dead on, but then it's easiest to see them when they're more edgewise. Composition is much like Jupiter's. It's mostly hydrogen and helium, and it's got other random little gases, and of course it's got every element in the periodic table, but just in really trace amounts. Again, mainly hydrogen and helium. That's the takeaway. Atmosphere, it's again kind of a question mark. Just like Jupiter, is there a surface? Is there not? NASA identified the troposphere to be this region here, and below that, that's the weather zone. If you remember, troposphere is the weather zone. And below that, you have ammonia and ammonium hydrosulfide ice and water ice. Again, you don't really need to know these, but they're different colors based on the compositions. It does not have extreme zonal flows like Jupiter. Jupiter has this kind of extreme band that goes to the left, and then another band that goes to the right, and an extreme way. Now, it does have some zonal flow, but it's not near to the extreme with the belts and bands that Jupiter has. Overall, it's the east-west flow. It does generate some weather. These are little storms. These are little clouds. They look tiny to us, but of course they're ridiculously massive. They tend to be short-lived. They're not like the Great Red Spot. These are some larger storms, right? These are quite large ones. So Tethys is a moon of Saturn. A couple other pictures of storms on Saturn. They're very, again, short-lived. They don't typically last long periods of time. You can see how the clouds are kind of moving as the planet rotates. Here's the zonal flow that I was talking about. I mean, you see a little bit of flux here and there, but overall it's kind of going in this direction here. So, slight amount of flux here, but it's not as extreme as Jupiter. If you remember, Jupiter's is going left, right, left, right, left, right, left, right. Not as extreme. The interiors, just like Jupiter, all Jovian planets have Jupiter-like interiors where they're kind of question marks. What exactly is in the middle, we're not quite sure. But we do know that it has lots of molecular hydrogen in the outer part, and then it has what we believe to be metallic hydrogen, or a type of hydrogen that takes on metallic properties that will generate a magnetosphere as it rotates around an inner core of something. Right. Comes from Voyager 1. Most of the stuff we know. The Cassini mission has revealed a lot more information as well, but that's a still ongoing mission as of 2015. But it has a metallic-like hydrogen in the outer core, so that's what we just spoke about. This causes it to have a magnetosphere, of course, and it obviously causes that, therefore causes aurora on Saturn as well, just like Jupiter. So these are just highly charged solar wind particles that are riding down very similar to the Van Allen belts. These are some early sketches of Galileo, by Galileo. Galileo was kind of confused. He thought it was a large planet with 2 moons. He wasn't quite sure what it was. He later revisited it and decided that it was possibly some kind of structure going around it, and didn't really understand the ring itself. Huygens, about 40 years later, comes back. He's a Dutch astronomer, and his big claim to fame is that he kind of identified the rings and possibly even some of the early ring systems. Saturn's rings. We're changing classes. B is the brightest one. It's the Einstein of the group. A is the dimmest and the thinnest. So I call it the Paris Hilton of the rings. They're mainly ice. There's some rocky material in there. It was probably at some point one of Saturn's small icy moons. The fact that it's ice causes them to be very reflective. These are what's called the main rings. You have the C, B, and the A. These are the first identified ones. So A is the thin one, right? B is the super bright one. I just mentioned that. C is very tiny comparatively. We've since named other rings. The Cassini division is this region here, and the ink gap is just like the Cassini division. It's just smaller. It's a region where there's no ring materials. So starting from the interior of the planet, it technically goes D, C, B. There's the Cassini division, A. Then the ink gap, then F, then G, then E. Now these were named in order of their, in the order that they were discovered. So originally we thought it was just A, B, and C. So we decided A in the outside, then B, then C. Then we later discovered the D. Then later missions have revealed the E, F, and the G. So just the order is not, although it may look alphabetic, it's definitely a little wacky. So probably what caused it is a satellite got tidally distorted to the point that it crushed it. This is obviously a theory. We don't know this. But as something gets closer and closer to a planet, it's going to become more and more tidally affected. And a planet that has as much mass as Saturn is definitely going to be tidally affected. And at some point, it can no longer maintain its spherical shape, and it will burst into pieces. And that's kind of what that's showing here. So, and this limit that ring material kind of will form and then eventually get absorbed into the planet is known as the Roche limit. So if it's outside this limit, a satellite will maintain its shape, but if it's outside of it, then it won't. So this is what I was just mentioning. Ring formation theory is an object about 250 kilometers in diameter. That's pretty small for a moon, but you know, obviously that's a lot of material to make rings. These are just showing ring comparisons to other planets. Jupiter not having but really one major ring. Saturn having multiple. Jupiter technically has two, but this is showing it in relation to the Roche limit. So these are the Roche limits of each planet. So you can see all these materials here from Saturn are going to eventually absorb into the planet. All these for around Uranus and Neptune are as well, except for this one right here with the Adams ring for Neptune. It may not. It's very, very close to the Roche. This is a size comparison of the rings to the planet Earth. So Voyager revealed more rings, the D and the E, and D is just a small ring inside the C. The F ring is located beyond the A, and it's formed by the debris shot up from the moon Enceladus. Just quick note here. Easy to remember this. E ring formed by Enceladus. Easy way to remember that. F ring was found after the E, and it's also beyond the A. So, I mean, this kind of alludes to the reason there's kind of this wacky naming. So you can pause the video here and look at this in greater detail if you choose. Purple are the rings. Starting here, you have DCBA, then you have FGE. So red is the planet, obviously, and green are the gaps, Cassini gap and the ink gap. The Cassini division is not completely empty of matter. It has some stray material that gets kind of thrown around in there, but it's for the most part clear. It's caused by the gravitational tug of Mimas, which is Saturn's innermost moon, and it kind of clears out the material in the Cassini division. F ring is very interesting. It's made up of what we believe is several separate strands that are kind of braided together. Here you can kind of see this here, this little bitty one here, and it's kind of braiding in with this one, and they kind of intertwine. It's kept together by two shepherding moons. It's Prometheus and Pandora. We'll talk about those in a second. There's one of the shepherding moons. Shepherding moons sound just like what you would think they are. There's a moon on this side of the ring and another moon on this side of the ring, and they kind of herd the material, the ring material, together. It's actually quite fascinating. So Pandora and Prometheus, they're very small, about 100 kilometers. They gravitationally play tug of war with the ring to keep it in place, right? So this moon will tug this way, and then this one will tug this way, and as a result, the ring itself kind of stays structured. It's just a little further explanation about the shepherding moons. We'll conclude with the moons of Saturn. Most of the moons are covered in ice and snow. It's very far away from the sun, so it's very cold, and it always stays very cold. Have 6 medium-sized moons with diameters about 400 to 500 kilometers. Titan is the second largest moon in the solar system behind Ganymede of Jupiter. And as of 2008, a total of about 60 moons, mostly captured asteroids. It's a list of some of the other moons, and again, you're welcome to pause the video and take a look at any of this information if you find it necessary. Titan is the most interesting moon of Saturn by most people's accounts. However, Enceladus is definitely kind of coming along as one of the more interesting ones itself. Titan was discovered by Christian Huygens in 1655. The Voyager 1 was reprogrammed to take a closer look at Titan, and it got sent above the ecliptic. If you remember, the Voyager 1 got sent above the ecliptic, and the Voyager 2 continued to go along the ecliptic past into the Kuiper Belt. So Voyager 1 took this shot up here. This is a very exciting shot because it kind of reveals this little blue haze right here, which really shows that Titan has an atmosphere. When we launched Cassini in 1997, it was the most sophisticated probe launched. It's still collecting data. It had this little guy right here attached to it, named the Huygens probe, after Christian Huygens, of course, who discovered Titan. And this little guy descended on Titan's atmosphere in 2005, and it took atmospheric readings, and it found the surface covered some kind of methane jello stuff. It's atmosphere is thicker and denser than Earth's. That's kind of crazy because it's a moon. It has a thicker atmosphere than a planet, which is kind of nuts. 90% nitrogen, 10% argon, and trace methane. So what you see is in many ways Earth-like. Earth, of course, has 70% nitrogen, about 1% argon. Of course, we have a lot more oxygen. So the surface temperature is extremely cold. It's about 94 K. That's about negative 250, negative 240 something Celsius. That's very cold. This allows methane to condense and rain. Here you can see these clouds of methane. Right? Methane on Earth is a gas. If you cool down any gas, it will eventually turn into a liquid and then a solid, of course. But it's so cold that it'll condense. It has smog-like layers. Photographed by the Voyager 1. That's this blue haze right here I was pointing out a minute ago. Some of the more medium-sized moons. This is Earth's moon over here, kind of size comparison-wise. Mimas looks like the Death Star, I think. They're mainly rock and ice, H2O ice too. A little bit of information about Rhea and Mimas. Interesting thing about Mimas is it causes the Cassini gap. It's a kind of a notable idea about it. Pictures of Enceladus. This is the surface of it. Beautiful moon. These are geysers that are rising up off of the erupting out into the outer space. Really, it separates from the planet. Possible cross section of it. We're kind of unclear what that is. Size comparison. Here you see the moon. Here you see the Earth. Here's Enceladus. Right. It's a fairly small moon. It's covered in ice and reflects almost 100% of the sunlight it receives. It's literally that color. I mean, that's the actual picture. It's white. Geysers spew H2O into the atmosphere. The H2O freezes instantly. A lot of it rains back down on the surface, which is why the surface is ice. But a lot of it separates from the planet and forms Saturn's E-ring. The E-ring is believed to be all material from Enceladus. This is another diagram of the shepherding satellites, Pandora and Prometheus. All right, I hope you found that useful.